times throughout this lecture I've been mentioning these sort of useful things that you ought to know exist, like max and range and numerator and zip and len. Where do we find out about these things? Part of that is the process of just learning the Python language. Most languages have features like this, and you just have to know, okay, this thing probably exists, and here's how we find it. So how do you get that knowledge to begin with? Well, part of getting that knowledge is classes like this, where you see people using these tools. And part of that knowledge is going to come from teaching yourself. So later today, I'll send out a couple links to some basic Python tutorials that are going to give you a sort of more rigorous introduction to, okay, here's a list, and here's what we can do with the list, and here's these other Python data structures that Mike talked about last lecture, and here's what you can do with them, and here's what they allow you to do. This list.append. Well, how would you have known that you could do a list.append? Or you could have a list and you could press dot and hit tab to see what a list lets you do. So let's try that. So data. Right, that's our list. So what can we do to data? Hit tab. Oh, we can append, we can clear, we can copy, we can count, we can extend. And you could, for any of these, you could do a question mark and get the documentation for what that is. But that's kind of sparse. So what you really need is a basic language reference and introduction to know what's out there. And so I'll send that to you guys later today, a couple good Python tutorials. So our hope with this course is that you're not going to walk out knowing how to do Python, or even necessarily knowing exactly how to do a simulation just like I showed. But you're going to know that the tools exist, and that if you thought about it a little bit, you could put something together to answer your question. Or you could ask someone to help you answer your question. You would have the right nouns and verbs to at least start the process. And so I think that's the expectation that you want coming out of this. Do I know enough to be able to teach myself? And so I'll send out some resources to help with that. Okay, so remember our simulation about the cancer mice. We wanted to know, okay, well, how likely would it be to get 4 mice or more cancer-free just by random chance? So that's one kind of potential random chancey thing that might happen. Remember, 40% cancer-free, just like the National Blueberry Council said, is twice the cancer-free rate of the baseline mice. So it's also possible that you could get a different kind of crazy, fluky result just by random chance. Where instead of twice the cancer rate, maybe we get half the cancer, or twice the cancer-free rate, maybe we get half the cancer-free rate. So maybe the question we want to ask is, okay, what's the probability of getting a result as extremely weird or weirder than what we saw? Not caring about the direction of the weirdness, just say, how likely is it to see something this weird in general? And so, okay, well, if this weird is either twice the cancer-free rate or half the cancer-free rate, what we need to do is go back and say, okay, well, we're interested if the blueberry eating is 40% of the 10 mice ate blueberries, or less than or equal to 10% of the mice. So that would be half the cancer-free rate. So this is probably a more fair way of asking this question. Not how surprised would you be to see a probability of mice this extreme only in the positive direction, but how surprised should we be to see this extreme at all, under the assumption that it really is just random independent chance. So let's rerun this analysis. Oh dear, as you might expect, our count went up because now there's more ways to increase this count, because it's not just greater than or equal to 4, it's also less than or equal to 1. So now 36% of the time we would have expected to see a result as extremely weird as we saw. So now we can really get the sense that, okay, a result like this is not extremely weird. Okay, so what I've talked to you about now is called the Fisher exact test. And it turns out, just like the question about what's the probability of getting 15 genes with 12 exons or fewer, you can model the Fisher exact test as a balls and urns problem, and you can solve it, as you might expect, exactly. So we could just use math to get these numbers beforehand. been convinced that this is the right way to ask the question. Because is there something a little suspicious in what we've been doing with our simulation? What's suspicious about this simulation?
You watch the cancer possibility? So you're only picking 7?
Yeah! Why are we only picking 7? That doesn't seem like how it's always going to go if we randomly do this. We're only picking 7 because we can do the math when we only pick 7. That's the Fisher exact test, and we can do the math that way. But when we do a simulation, we're not slaves to doing the math. And so here's an example of where we can ask the question without having to be able to do the math in some clever way. Okay. All right, so what are we going to do? Let's copy this and modify this. So we're going to say for I in range 10,000. So we want to assign cancer to the mice randomly. What probability do we want to randomly assign a mouse to have cancer with? Or cancer freedom. Instead of assuming that always 7 of the mice are cancer free, we're going to say that each mouse is cancer free with a 7 out of 25 probability. That makes sense? This is what we saw originally, that 7 out of 25 of our total mice are cancer free. And so what if that was the rate? We just sort of randomly assigned cancer to the mouse with that probability. All right, so let's do that. All right, so for mouse and mice. All right, so how are we going to choose the mouse if the mouse has cancer or not? Well, we're going to draw a random number from 0 to 1, and if it's less than 7 out of 25, we're going to say, okay, that mouse gets cancer with that probability. Does that seem reasonable? Now I happen to know, and you could check, and you could read the documentation for numpy.random, and it would tell you all the stuff that's in numpy.random, or you could do numpy.random ? And see the tab, the documentation, or numpy.random, hit tab and see all the list of the things that are in there. And then, you can read around, and I have read around, and I've found that random.random gives us a random number between 0 and 1. So if random.random is less than 7/25, that mouse was cancer-free. So what we want to know is we want to know how many mice were cancer-free. So okay, so if this event happens, we have a cancer-free mouse. Now we further want to know if the mouse was a blueberry eater or not. Okay, so I better set that to 0 at the beginning too, right? Otherwise, there's going to be a problem. Okay, so now we have a list of how many mice got cancer and how many of those mice weren't eating blueberries. So what do we want to compare that to? Should we say if it's greater than 4 or less than 1? Reasonable, we could do that. Another possibility no cancer blueberry eater is greater than or equal to 4/7, so that was our original ratio, but the original ratio is only relevant when we have 7 mice with cancer. So let's multiply that by the total number of mice with no cancer. And then we'll do, less than or equals 1/7. So this is sort of a matter of taste. Do we want to ask if there are more than 4 mice or fewer than 1 mouse, regardless of how many got cancer, or do we want to ask if the ratio of the mice without cancer was bigger or littler than the ratio that we would have expected by chance? We could do it either way, and it's answering a slightly different question. Let's do it this way. Maybe I should write. Oh, yeah. We need to do something about that. We got to add one to the count of the events that happen. Okay. So if we set up the problem like this, it says, okay, 23% of the time do we get a result that's that unbalanced, one way or the other, from the ratio that we would expect. All right, so what's going on? We did 3 different simulations, and they all have slightly different assumptions about the questions we're asking, and we got 3 different numbers. Well, the good news is none of those numbers was small. All of the time, all of the simulations we did, it said this is a pretty routine occurrence. And so this is what we want. Simulation lets us test many options and many assumptions, and you want to see that they're all telling you the same thing. If, on the other hand, what if we got disagreements? What if we came up with a sort of reasonable sounding set of assumptions that we simulated and said, oh, only 0.5% of the time would you expect this particular occurrence to happen. And all the other simulations you did with slightly different assumptions say, oh, this is totally routine. What do? What you do is you say, data, you're drunk, go home. What you don't say is, data, would you like to dance? You don't want your data waking up in some journal that it doesn't remember about with your name attached to it. So, what you don't do is, okay, I'll just report this one simulation, this one set of assumptions that gave me the answer that I was looking for. What you do, what you do is you use this as a sanity check. Am I fooling myself? And if you get a disagreement in your simulations, or a bunch of simulations that say one thing and some that say another, the chance of you fooling yourself is really high, and you don't want to run that risk. Don't fool yourself. These simulations, they might be useful to report in a journal. You might need to report them in a journal. We'll talk a little bit this lecture and more next lecture about p-values and hypothesis testing, and some of you probably are already seeing how this is really basically getting to p-values. But really, as I emphasized at the beginning of this course, these tools are to help you convince yourself that you're not deluding yourself. These tools are to help you convince yourself that the data are real, to encourage you to go back and do real biology experiments and not more of the statistics, data dredging stuff. Okay, so I'm gonna end with sort of a parable. So, as I mentioned, many of the problems that we talked about could have been solved just by using math and logic. Obviously the logic answer to the Monty Hall problem is sort of satisfying and clear once the setup is done. And obviously, having a formula for figuring out the probability of getting 15 genes, all with 12 exons or fewer, is a little more satisfying than having some simulation that, takes a while to run and gives you a slightly different result every time. So almost everything we've talked about could be solved. Closed form, end of discussion with math and logic. The simulations that I've showed you only gave us approximate answers. So a parable about this. Does everyone know what a Dremel tool is? Raise your hand if you know what a Dremel tool is. Okay, so a Dremel tool is sort of like a drill, and sort of like a saw, and sort of like a bunch of things. It's a little tool that spins some kind of blade around really fast. My mom used to do high-end carpentry and woodworking and worked in a cabinet shop. And so she knows a lot about, how you do things right. And so when my brother-in-law asked for a Dremel for Christmas, she had no idea what a Dremel was. And I was like, well, why does someone who spends so much time around wood and woodworking not know what this simple, common woodworking tool is? And then I realized she didn't know what it was because a Dremel is never the best tool for the job. There's always a better tool than a Dremel for doing any particular task. But the virtue of the Dremel is it is always the second best tool for any job. Anything that you need to do, you can figure out a way to use this stupid little thing to cut or sand or polish or whatever you want. So in some sense, simulation is kind of like that. It's almost never going to be the right answer, but knowing how to do a simulation is always going to get you pretty close in the right ballpark if you do the simulation a bunch of times, pretty unimpeachable. And it's a whole lot easier than learning a bunch of different special case math. This is one sort of universal tool that you can have in your holster to ask a whole bunch of different kinds of questions about, or kinds of questions with. So that's why I'm hammering on simulation and learning how to ask questions in code. So you remember what Mike talked about was pseudocode. You know, we write down what we want to do in English, and then we try to translate that into code. And the simulation business is pretty much the same. We write down the process that we want to happen, and sort of think about it. And they say, okay, here's what I want to happen. Now I'm going to write code to make this process happen. And we're going to do that a bunch of times with slightly different random conditions and see what we get. And that is almost always going to give you the right answer or something close enough to it that you're not going to be led astray. In a way that, as we saw, as I said, many statistics professors got led astray by this Monty Hall problem. But I don't think anyone who wrote a program to find out the answer got led astray. So with that takes us to the end of this lecture. In 2 weeks is the last statistics lecture. And what we're going to talk about then is null hypothesis significance testing, otherwise known as p-values. How do we get p-values? Where do p-values come from? What do they mean? Can we use the simulation tools to get p-values in a variety of different contexts? And how do we use that to interpret whether or not our data are actually showing us something real? This is what we've been going through this whole time, so I hope everyone's really excited for p-values.